Okay, this is example from section 17.7 where we used the equations to calculate the planes, the normal stresses, the shear stresses, and the principal stresses and the principal plane orientations. So given the stress element shown right here, find A, the normal and shear stresses at a 60-degree plane, B, the principal stresses and their orientations, and then C, the maximum stresses and its orientation. So the solution, first of all, we know our sigma in the x direction is 10,000 psi compression. The stress in the y direction is tension, 13,000 psi in tension, and the V, the shear forces, the shear stresses are negative 7,000 psi. We'll get to that, why I mean negative, in a second. Normal stresses at 60 degrees. The normal stress at 60 degrees, what we're going to do is just plug in equation 17.6. That is the stress on the normal. The normal stress at 60 degrees is, here's your equation, I plug all that in, and I get 13,300 psi positive. The shear stress at 60 degrees, I plug in equation 17.7, and I get negative 6,460 psi. And then what are the principal stresses? Principal stresses are, using equation 17.9, I plug in my values, and I get 1,500 psi plus or minus 13,460. Therefore, my principal stress is F1, which is my highest stress level, which is 14,960 psi. That's in tension. And then my other principal stress is the negative of that, and it's going to be in compression. Okay, 1,500 minus the 13,460. So those are our normal stress at 60 degrees, shear stress at 60 degrees, and also our principal stresses for this element. This gets pretty hairy sometimes in terms of trying to figure out what the angles are for the principal planes using these equations. So I'm going to walk through this one just so you can see what's going on with it here. Okay, so we have equation 17.8. This equation right here, that tells us what the tangent of 2 theta p is. We need to solve that to find the orientation of the principal planes. Okay, so first of all, this is negative right here, okay? So you can't really just solve for 2 theta p because 2 theta p must lie in either the second or the fourth quadrant, since tangent 2 theta p is negative. So if we're looking at the tangent function here, that's what it shows us. So really what we need to be is in this quadrant right here, or in this quadrant right here for this to be valid. So how we're going to do that? If 2 theta p were in the first quadrant, that would be at 31.34 degrees. In the second quadrant, it would have to be actually 180 minus that 31.34 degrees, which gives me 148.66. Then you divide that by 2 because all of these angles are in terms of 2 theta p. So that gives me 74.33. And then we have to look at it in the fourth quadrant as well. And really, to get our maximum planes, we have to substitute these equations. We have to substitute to 74.3 degrees back into this equation right here to tell us whether or not we guessed right, and then to see if we come up with this stress here, principal stress 1. So it can be a little bit hairy, but what we got is 74 degrees, and then 164. Now the max shear stress, what we have here is our equation 1711. We plug that in, and that gives us our maximum shear stresses. And then the normal stress at the maximum shear plane, equation 1712, it gives us 1,500 psi. Okay, I'm going to stop this one here, and I'm going to pick up the example from section 17.8 after this.